All right. Okay. Today we are going on with our methods for non-linear regression, methods that include non-linear capabilities in our regression functions by introducing smoothing splines. As you can see by the symbol of the uphill car, this is a bit more mathematical than other topics, but this should not bother you too much because really we will keep things as simple as possible. Now, smoothing splines, they share the name with the splines we have already seen, but the way they are estimated is based on a completely different approach, as we will see in a minute. Therefore, the splines that we have been studying so far, they could be named regression splines, while these ones are smoothing splines. What's the main idea behind the smoothing splines? The idea is finding a smoother, a regression function, by solving an optimization problem. And you can see here the optimization problem. So you want to minimize the sum of two terms. The first term is the usual residual sum of squares, as you can see. So it's a measure of the fit to the data. And the second term is a kind of roughness penalty, regularization penalty, where you can see there is the second derivative of the function. So you are looking for a function g of x that should perform your regression, and you are putting a penalty on the square of the second derivative of g. And what does it mean? The second derivative is meant to measure the roughness of the function. So if the function is oscillating, then it will have large values of the second derivative. As a matter of fact, the second derivative is also used as a measure of the curvature of a function. So we are looking for a function with a small curvature. And the trade-off between the two objectives, so the first objective is data fit, the second objective is smoothness, low curvature, is controlled by this parameter lambda that is a tuning parameter. Okay, and okay, I've already explained these things. This is a non-negative tuning parameter, and the idea is that if you take a very small value of lambda, then you will find a function g of x that goes very close to the data. For lambda tending to 0, you will eventually perfectly interpolate your data. While if you increase lambda, then g will become more and more regular, and in the end, if lambda is really very large, you should obtain a function g whose second derivative tends to 0. But what does it mean, second derivative equal to 0? Well, it is a linear function that has such a second derivative, and this means that if you increase lambda very much, in the end you will turn back to linear regression. So this is quite nice because you have a flexible method in which you can control the amount of regularity by means of lambda, and you can go from two extreme solutions. Extreme one, that you are fitting the data at the cost of having something which is very wiggly, very oscillating, and the other extreme is that when you push lambda to very large values, then you will have a regression function that is more and more similar to a linear regression. So this is okay as a method, and okay. As a matter of fact, this appears as a rather complicated mathematical problem, because think of it, you are not assuming that g belongs to some family of functions. So I'm not assuming that g is a polynomial with some set of parameters, or it could be a linear combination of sines and cosines, nothing at all. I just consider a very generic g of x. So you could think that it's very difficult to solve this kind of problem. So how could I find among the infinitely many possible functions the one that minimizes this cost function? It seems a kind of impossible mission, as a matter of fact, but quite surprisingly, it comes out that the solution is not that difficult to find, and moreover, it has a very definite structure. As a matter of fact, the solution is a natural cubic spline, something that you already know, okay? And you know that natural cubic splines are piecewise cubic polynomials. This means that you have many cubic polynomials in different intervals, and where you go from one interval to another, you have the so-called knots. So, and in the knots, you have a discontinuity in some sense, but there are constraints such that the value of the piecewise polynomials on the left and on the right, and also the first and the second derivative, are equal. In this way, you have two different polynomials, but the connection is something that is very continuous, not the third derivative, but until the second derivative you have continuity. And therefore, okay, we get a cubic spline, and the question, of course, is where are the knots if this is the solution of our optimization problem? And the surprise is that this is a cubic spline with a very large number of knots, because you have a knot at every value of xi. Xi is the x value of your observation. So if you have 100 observations, these will be pairs x1, y1, x2, y2, x3, y3, and so on. And if you solve that optimization problem, in the end, you will get a cubic, natural cubic spline with a number of knots equal to 100. So this seems a huge number of knots, and it would seem that you have a model which is largely overparameterized, because we know that cubic natural splines have a number of parameters that is equal to the number of knots. So in that case, if you have 100 observations, your smoothing spline will provide you with a natural cubic spline with 100 knots, and that amounts to 100, a model with 100 degrees of freedom. But this is not true. So it is not true that this model is overparameterized, because the key point that you should keep in mind is that you are not estimating the parameters by least squares, but you are estimating your parameters by minimizing this cost function. So thanks to the regularization parameter, okay, you are able to keep under control the roughness. And so even if you have so many knots, your estimate will be rather smooth. And this smoothing spline has a definite advantage on the splines that you already know, because a major problem with the usual splines, I've told you that they should be called regression splines, is that you have to solve the knot selection problem. So you have to decide how many knots you are going to use, and also you should decide where you would like to place them. Instead, in the smoothing spline problem, everything is automatic. So you just start from the optimization problem, and you will end with a solution that depends only on the value of lambda, that decides the flexibility of your regression function. So this is a very attractive property. We are not going into the algorithmic details, although they are not really so terribly complicated. Indeed, it can be shown that the numerical computation of the smoothing splines amounts to the solution of a system of linear equations. So if you have 100 observations, in the end you have to solve a system of 100 linear equations, which is something that you could do quite easily. So that's nothing terrible, I should say, and this is really a good property of this smoothing spline regression method. If you are using R, you can find, of course, programs that are ready to be used. Once you have fitted your smoothing spline, then you can get the predicted value, and in particular, you can get the predicted value in correspondence of the training data. And these are computed as a matrix. This is a square n by n matrix, S lambda times y. This matrix is important for two reasons. First, because once you have it, you can obtain the predicted value. But more importantly, it is helpful to assess the degrees of freedom of your smoothing spline. As a matter of fact, if you are performing regression by smoothing splines, you will have to choose the regularization parameter lambda, and it might be you obtain lambda, say, equal to 1000. Is this a large value? Is this a small value? I cannot answer, because if you give me a value of lambda, it is not possible, it is not normalized, so it is really very difficult. It depends on the measurement units, on the problem, on specific features of the problem. So the lambda is not a meaningful measure of the regularity and of the flexibility of the model. So it is very useful to have a measure which is really easy to understand, and this measure is given by the degrees of freedom. So you can just take this matrix S of lambda, and if you compute the trace, you should recall that the trace of a matrix is the sum of its diagonal entries, and this is what I'm doing here. If I compute the trace, I obtain a real number that can be regarded as the degrees of freedom of my smoothing spline regression. So this is quite useful because, for instance, if I am fitting 50 data and I compute this df of lambda, and df of lambda is equal to 4, this means that my smoothing spline has more or less the same flexibility of a 4-parameter polynomial. A 4-parameter polynomial is a cubic polynomial because you have the intercept and then you have 3 coefficients for the powers of x, and then you understand very quickly how much flexible is the model you are using. And so this is a nice possibility of having a measure which is somehow normalized, because the degrees of freedom that you obtain, they cannot be larger than the number of training data. And also, if you are using R, in MATLAB, unfortunately, it was not possible. I don't know if in Python is possible. You can directly specify the degrees of freedom instead of lambda when you are performing smoothing spline regression. So instead of fixing the value of lambda, and usually you cannot guess lambda, you have to go through some tuning, usually by means of cross validation, but we will see in a few seconds. But you could just start with the degrees of freedom. So if you think that for a certain data set the flexibility of a cubic model is okay, then you will specify that you are using a spline. Here degrees of freedom equal to 10, but if you want the same flexibility as a cubic polynomial, you will let df degrees of freedom equal to 4. Okay, in general, you will have to calibrate the value of lambda, and you can use the methods that we already know. So you could use cross-validation, k-fold cross-validation, and there is also the possibility of using leave one out cross-validation, that is k-fold cross-validation with k equal to 1, Okay, and in in the leave one out cross validation, you know that you are keeping apart one observation, you train the model on the remaining n minus 1, and then you try to predict the observation that was kept apart. And then you repeat, you take the second observation, you leave it apart, you train the model and try to predict this one. So it would seem that you have to perform n steps to compute leave one out cross validation, but you know that there is a shortcut, at least for linear regression models, and which is given by the leave one out lemma. Well, as a matter of fact, the leave one out lemma holds also for smoothing splines. So you can compute the cross-validated leave one out cross-validated error just by performing a single estimation. So for a given lambda, you compute your smoothing splines. In particular, you compute the prediction g hat lambda of xi, and here you have the residuals, and then you compute this sum of weighted squared residuals. So these squared residuals are weighted by this term, and here you can see the diagonal entry, the ith diagonal entry of matrix S. This matrix X is also called the hat matrix that we had already met when we introduced the leave one out lemma for linear regression. And therefore you just perform one estimation for a given lambda, and by this formula you get the cross-validated error. Then you can iterate for different values of lambda until you minimize the value, the cross-validated error, and that at that point you will have the optimal lambda that you want to use. Okay. But let's see how it works in practice. So this is a smoothing spline. Here we have two curves. The first one is with smoothing splines with 16 degrees of freedom. The second one with 6.8 degrees of freedom. And this value of 6.8 was found by applying the leave one out cross validation criterion. Pair of observations, you can see that they are quite similar, although the blue one, having less degrees of freedoms, you can see that is more regular, so you don't have some oscillations that you can see in the red curve. The other interesting fact is that you have 6.8 degrees of freedom, and this could seem a mistake because you see how can it be that the degrees of freedom are not an integer, but as a matter of fact, for smoothing splines, this is well possible because you should go here. The degrees of freedom is just the sum of the entries on the main diagonal of the hat matrix, and there is no reason for these entries to be integers. So as a matter of fact, when you compute this trace, you will find a real number. Therefore, it is possible, for instance, that you have degrees of freedom that are in between 2 and 3, for instance. So what does it mean? It means that your model has a flexibility that is somewhere in between the flexibility of a line, 2 degrees of freedom, and the flexibility of a quadratic model, 3 degrees of freedom. So you can have intermediate degrees of freedom that you couldn't have with polynomials. If you are using a polynomial, the degrees of freedom will jump from one integer number to another. Of course. Okay. That's all for smoothing splines. We now say a few words on another interesting technique, which is called local regression. Its name is lowes, and it can be written in two ways. One way is this one, lowes, here, and there is another writing in which you have a W in between, but more or less they are the same thing. And the idea is that linear regression is going to perform well locally. So the idea is that if your regression function is to be quite regular, then you should get a good result in a neighborhood of some point by performing a linear regression on the data that are in that region. So for instance, let's see, here you have the data, you are interested in some good approximation around here, so you take the red data, so you take the data in the neighborhood of the point you are interested in, and you perform a linear regression, and you obtain this result. Then you will not use this linear regression everywhere, but you will just use it in correspondence of the central point. So this linear regression tells me what is the prediction here. If I'm interested on giving predictions in another point of the x-axis, for instance here, I take the red data here, I perform a linear regression on the red data, and as you see, I get a linear regression which is completely different from this one, okay? And still, I'm not going to use it far away from this point, but just take the prediction that it gives me in this specific point. So the idea is exactly this one, is to perform a local linear regression. You could also go for quadratic, for a polynomial regression, but the idea is that linear is possibly the best choice. So you perform a linear regression on some data around the point you are interested in, and once you have performed the regression, you just keep the prediction that the regression is giving to you. Then I move along the x-axis and I will perform a new regression, and again I will keep just the prediction that the regression offers me in the central point. Two details. First detail is that not all the points are going to be given the same importance, but I'm using a weighting function. The weighting function is represented here by this yellow curve, and the meaning is that the points that are very close to the central point are going to have maximal weight, while as I move in this direction and in this other direction, less weight is given to the points according to this function. There is also another parameter that determines the percentage of points that I'm going to use for my local regression. For instance, here you could guess that this number is about 1/3. So when I compute the lowest here, I'm using 1/3 of the data, and precisely the 1/3 of the data that are closest to the point I'm interested in. Okay, this is a quite general method. It performs quite well. Usually you will get something which is similar to regression obtained by smoothing splines. And the advantage is the flexibility. The possible drawback is that you do not get a function that is that has a closed form expression. So differently from polynomial regression, you just obtain a curve, but this curve could not be represented by a simple formula or a simple expression that can be communicated easily to someone else. You just obtain your curve, but in some cases this could be enough. Okay, let's now discuss the final topic of the chapter, that is generalized additive models. The idea of generalized additive models is to keep the best from linear regression and the best from nonlinear models. So we like linear regression because of its simplicity and because it it's easy to interpret the results. So you have coefficients for each variable, so you can see what is the effect of a variable, positive, negative. You can also have an idea of the size of this effect, and you can also test if this effect is statistically significant. On the other hand, we have said that reality, the real world, is not linear, almost never linear, and therefore we need some more flexible methods, and therefore we introduced polynomial regression, cubic splines, regression and smoothing splines, and also the lowest regression model. But how could I retain the advantages, the simplicity, the ease of interpretation of linear regression, and at the same time introduce the flexibility I need? The answer could be by means of the use of generalized additive models. The structure of a model of this kind is represented here. So here you have the response, and here you have the intercept, okay? And then here you have several functions. This is a function of x1, this is a second function of x2, and so on. And these are nonlinear functions. Okay, so the fact that they are nonlinear, this allows a greater flexibility. So you are able to accommodate also dependencies that are not linear, of course, but there is a feature that is preserved, that is the fact that you have a sum of additive terms. So you can know who is responsible of what. So in this predictor, you know that this is the contribution of the first variable, this is the contribution of the second variable, and so on. And more importantly, this contribution is not forced to be linear. In the old good linear model, here you had beta1 x1. Here instead you have a function which could be arbitrarily complex. And also you can present the results in a very meaningful way. So this is an example where you have an additive model, and then you are going to present the results showing how the response depends on the variable year, how the response depends on the variable age, and how the response depends on education. Okay, and okay, you have here, you can see that this is not linear, so these are nonlinear functions, but you can also introduce confidence bands, which is also useful because in this way you can understand how strong is the effect of one feature on the response. What's the limitation of these models? Because it would seem that they are really extraordinary. The limitation is that, of course, this is not the most general function you can imagine, because here you could have that the response depends on both x1 and x2, and you cannot simplify the dependence on the two variables as the sum of two terms, as I'm doing here. So here I'm assuming that the function explaining how the response depends on these features can be decomposed into additive terms, each of one depends on one variable at a time. So to complete this approach, we need methods to take into account of the interactions. Okay. But we will talk about this in a few seconds. These are called generalized additive models. You can fit them, here it is in R quite easily. So here you want to fit a model explaining wage, and you do this with three terms: a natural spline term depending on year, a natural spline with 5 degrees of freedom, a natural spline term depending on age with 5 degrees of freedom, and then a linear term depending on education. Okay, we are not interested in the single coefficients, but in the functions. But we have already seen that functions are these ones and can be really interesting. For instance, if we are explaining wage, we can see that wage increases with age, and after a certain age it is going to decrease. So this is quite meaningful interpretation. That's really really good. Here education is categorical, so depending if you went to the university or not, you have different values, levels of wage. And here, this is the year, you can see the wages in general went increasing from year to year. Okay. You can do a lot of things in the sense that you can introduce linear terms and nonlinear terms in the same model. You can also use the ANOVA technique for comparing models, but we are not going into these details. You can use as well smoothing splines or local regression as the lowest. So here you could explain wage using a smoothing spline with 5 degrees of freedom, a lowest with span 0.5. This is the parameter that decides what fraction of data you are using for your local regressions. And then here you are using also education. What about interaction? That this is the weak point. Well, as a matter of fact, you can introduce interaction by adding terms where you take into account two variables at a time. For instance, you could put an additive term which depends on the product of x1 and x2. Or a more sophisticated approach, you could use a bivariate smoother. So you could introduce an additive term which is a bivariate spline, for instance, that depends on two variables. Here you are using what's called a tensor spline. This is a spline that depends on two variables. So as a matter of fact, it gives you a surface which is a tensor spline of natural spline type, depending on age and on year. Finally, good news, you can use a additive model, generalized additive model, also for classification. So here you have the logic transformation, and the trick is that instead of having a linear model here, you are just putting an additive model where f1, f2 could be rather flexible nonlinear functions. Here you are trying, for instance, to classify when wage is greater than 250, and this is what you will find with your confidence intervals. Well, I think that at this point we are done. Thank you.